Hello friends, I am Sanmitra Bhaumik and in today's lecture we will start friction. This is the introduction to friction and already I had earlier talked about friction in our previous lecture of free body diagram. If you have not watched that lecture, please go and watch because there I have given you the basic introduction about friction and how friction force works, acts. Like in an object which is placed on a rough surface and some forces are acting on it, then at which direction will friction force occur? So I have explained that in details in that lecture, so please go through. And in this lecture we will be analyzing friction on a deeper level. So let's begin. What is friction? Friction is the horizontal component of the reaction force on a rough surface. We have already discussed this. Like there is a surface and that surface appears smooth on naked eye. But when we magnify it, we can see the roughness on that surface. Like it is not smooth, it is rough. The surface is uneven. So exactly that is the cause why we encounter friction. See in this picture, let me show you. In this picture I have shown the rough surface. This is a magnified version of the surface and this is a magnified image, and I have kept a block, an object. This object is kept on a rough surface, and when I am pushing this object this side, say I am pushing this object this side, then what will happen? There will be reaction force from the ground, and that reaction force will be like this. Why it will be like this? Because at this point, the point of contact, the tangent of the surface, if I can say, this tangent will not be straight. In case of smooth surface, what will it be? It will be straight. But here it may be straight, it may not be straight, and mostly it is not straight because it is encountering. See here the reaction will be something like this on this object. This is very self-explanatory, but still I am trying to give you an idea. Now due to this reaction force, see, I will have a reaction force on the object from the ground, and an equal and opposite reaction will be acting on the surface. These two will be in line. In this picture I cannot draw it in line because of the limitation in space, but actually both will be in line. Now let's focus on this one. All these things I have explained in free body diagram lecture, so you can go that if you can go through that if you face any problem. See, this is R, the reaction force. I am resolving it into two components. One is the vertical component, that is the normal reaction. Other is the horizontal component, that is F. So this horizontal component of the normal reaction, that means when I am pushing an object on the horizontal direction, I am facing some friction, I am facing some obstruction or some reaction force that is acting in the horizontal direction. That is exactly what is known as friction. So what are the types of friction? There are three types of friction. One is called static friction, the other is the kinetic friction, and other is fluid friction. What is static friction? Static friction is when no relative slipping occurs. Like I am telling you, you have an object of, say, it is 100 kg. You are keeping it on the ground. Say you have another object that is 10 kg, and again you are keeping both of them on the ground. And now what you are doing is that you are trying to push both the 100 kg object and the 10 kg object. So when you are pushing the two objects, say you are using your maximum force or you are using the same force, which one will require, say this is F1, this is F2 to move it off the ground. So which one will require greater force, F1 100 kg block or 10 kg block? See, you can feel it because it's a very generic and common problem. Definitely what is heavier will require more force to move because it will encounter greater friction. This is F1, say, and say this is F2. So definitely what is heavier will require greater force. It will have to overcome greater friction. Until it moves, it is in static friction. It is encountering static friction. And after it overcomes the static friction, it will start moving. This 100 kg or say 10 kg whatever, this will start moving. This 100 kg block, this will start moving, and I'm applying this force F with an acceleration A, but there will be a friction force always, that is due to the ground, and that will be kinetic friction. That is, it is slipping with respect to the ground, so it is kinetic friction when slipping is occurring. And another type of friction there is, that is called fluid friction. Suppose I have a tube which is filled with water, and I am firing a bullet inside the tube. What will happen? The bullet will slow down and will fall. Whereas in case of air, the bullet will go up to a long distance, then it will fall. Why? Because fluid friction of water is very much higher compared to fluid friction of air, and fluid friction is dependent on speed of the object. But in case of static friction and kinetic friction, it is not dependent on speed. Also, fluid friction is dependent on the surface area. That is also not the case with static friction and kinetic friction. We will learn everything about fluid friction in a later chapter called fluid dynamics. Currently our focus will be on static friction and kinetic friction. So what is static friction? Static friction is the force acting on an object, or the force acting on an object not sufficient to cause the relative motion with respect to the contact surface. That means I am applying a force on an object. Say this is the block. I am applying a force. This force is not enough to move this object, so it will stay. I am slowly increasing the force. And I am increasing. Say the force is 5 Newton and the object is not moving. I am slowly increasing it to 6 Newton. Then also not moving. 10 Newton. Then also not moving. But suddenly I am increasing it up to 10.1 Newton. The object starts to move. So there is a limit up to which I can increase the force, the applied force, and the surface can hold that, or the surface can provide the static friction enough to prevent slipping. That is called the limiting friction. I will be discussing it later in the next part, in next a few minutes. But understand what is static friction. Static friction is a self-adjusting force. That means when I am pushing something, I am getting an equal and opposite horizontal reaction. That is static friction. Exactly just like normal reaction. What was normal reaction? Suppose I have a surface like this and I am keeping a block of mass m. I am applying a force F on the block. And also mass mg is acting here. Weight mg is acting here. Now the normal reaction from the ground will be n, and I can write n is equal to mg plus f. Now mg is constant. If I increase f, this block won't go into the ground because the normal reaction, it is supporting the block on the ground, so n will also increase. So n is a normal reaction, is a self-adjusting force. Similarly, I can also say, if I am applying a force, say F dash, this friction force in case of static friction, I mean this F dash is not enough to overcome the static friction. The static friction will not be overcome and the block will not slip. So I can say F dash is equal to F. Say our limiting friction is 10 Newton. If I apply 5 Newton, then F will also become 5 Newton. This side 5 Newton, This side also I will get 5 Newton. If I apply 10 Newton, I will get 10 Newton. But if limiting friction is 10 Newton, and if I am applying more than 10 Newton, say 11 Newton, then I will not get here 11 Newton. I will not get 11 Newton, I will get something less. What we will get, we will discuss it later. Okay. So this is independent of contact surface area, as I have already discussed. And see the graph. This graph is important. This is the friction force, and this is F. This is F, and this is the friction force. And whatever force I am applying, I am getting it as friction force. See, it is 45 degrees. So this length and this length is equal. So whatever force I am applying, I am getting it as friction force up to a certain limit. And that limit is F max. That is a maximum friction. See, we can write it friction as F is less than or equal to mu s into n. See, F max. This is the maximum friction, that is mu s into n, where mu s is the coefficient of static friction. Coefficient of static friction. I have written it here. So just I want to say one thing. F, I cannot write F is equal to mu s into n. This I cannot write. I have to check, I have to calculate that what is the value of F. Is it the limiting case? I can say F is equal to F max is equal to mu s into n. And I can write F is less than or equal to F max. So F max is less than or equal to mu s into n. There are many students who make this mistake. That is, F is equal to mu s into n, they write. But that is not true. We have to find out. Because F may be less than mu s into n. Okay. Now limiting friction, the maximum value of friction a surface can support for a given value of normal reaction. Beyond this, the object slips. That means if I apply a force that is greater than the limiting friction, that means the greater than the force, that is the support, greater than the friction force that the surface can actually support, then it will start slipping. So what is F max? F max is mu s into n, that I have already discussed. Now let's analyze a case. Static friction acting on an object on an inclined plane. See, this is a rough inclined plane, and we have an object M on the inclined plane, and this is rough. This surface is rough with a coefficient of friction that is mu. Let's say it's mu s. If not, they have asked us to find out static friction, so I will consider it as mu s, and the angle is theta. Now let's analyze. See, let's draw the free body diagram. If you are not comfortable in drawing free body diagram, then please refer to our previous lecture. And this is the block M. Now let's analyze the forces on it. I am just analyzing the forces on this block M. This red line I am drawing, that is only to denote the surface. Wait, let me draw it with dotted lines. I have drawn it with dotted lines just to show that that is not the object. See, this is the normal reaction in. It is moving downwards. It has a tendency to slip downwards. So friction will act in the direction that is upward the inclined plane. All these things we have discussed earlier in our previous lecture. Now mg will act vertically downwards, and we can resolve it into two components. One is mg cos theta. See, this angle will be theta, mg cos theta, and this will be mg sin theta. So we have drawn our free body diagram. Now I have drawn it again in a neat manner. After drawing the free body diagram, this is n and this is mg cos theta. These two will be equal. So mg cos theta is equal to n. This is F, this is mg sine theta. So mg sine theta is equal to F. For limiting friction, see they have asked us to find limiting friction. That is why I am writing F is equal to mu s into n. Suppose it was not limiting, then what would have been F? F would have been just mg sine theta, and n would have been mg cos theta. F would not be equal to F is equal to mu s into n. No, this is the limiting case. That is why I am writing F is equal to mu s into n. Mg sine theta is equal to mu s mg cos theta, mu s is equal to tan theta, and theta is equal to tan inverse of mu s. This is the limiting. Now see. Now suppose, let's say mu s is equal to, say mu s is equal to 0.6 or say 0.6. So if mu s is equal to 0.6, what is tan theta? Tan theta is 0.6, that is 6 by 10 or 3 by 5. So you can see theta is somewhere around some 68 degree or like that. So just this part, let me show you something here. Suppose, let me give you an example. Let me say, let's take mu s is equal to 0.75, a relatively high value of mu s. Say, let's say mu s is equal to 0.75. Now let's find out this angle theta. Tan theta is equal to 0.75, that is 3 by 4. So this is 3, this is 4, this is 5. Now we can say this angle is 37 degree, approximately 36.6 degree, so that is 37 degree. So for this value of mu s, our maximum angle can be 37 degree. Suppose the inclined plane is 40 degree, so it is 40 degree. Now if I place an object here, it won't be supported by the inclined plane, it will start slipping. But here in this plane it will not slip, rather it will stay, because the friction force is sufficient to support this. So this is called angle, this is an angle of repose. This is called angle of repose. It is tan inverse of mu. So if I increase our angle, then the object starts slipping. Okay. Now let's analyze kinetic friction. Kinetic friction is when relative slipping will occur. So relative slipping is occurring, that is kinetic friction, we have already discussed. It is not dependent on the contact surface area or velocity. So it is not dependent on the velocity of the block, and it is not dependent on the contact surface area. It is less than the limiting friction. This I will explain. Exactly what do I mean by that? Suppose I have an object of mass m. I am applying a force F. This force F is being, say, countered by a friction F. I am slowly increasing the force F. Initially it is in static equilibrium. I'm slowly increasing. I'm increasing up to the point, just see here, I'm increasing up to the point when F is equal to F max. Till that time, this block is in equilibrium, static equilibrium. Now, when I'm increasing it further, this F I'm increasing further, there is a sudden drop in the friction force and it becomes constant. And this is due to the fact that this block starts slipping. Now this is no longer in static equilibrium, or rather equilibrium. This will start slipping, and the net force will be in this direction, F minus small f. That small f is kinetic friction, and for kinetic friction I can say F is equal to mu k into n. This is what I have written here. So this value of kinetic friction mu k into n, that is less than the F max. It is less than the limiting friction, because we have to overcome that limiting friction to set the body in motion. So exactly this is what I wanted to say. Mu k is less than mu s. So I hope you have, this graph is also clear. Up to this part I have already explained. Now suddenly there is a decrease. This, to account for this decrease, we can explain that, we can infer that the value of kinetic friction, that is less than the limiting friction. So it is easier to keep a body moving than to make it move from rest. Suppose I am moving a block with a, say, velocity v, that is easier than to make it move, that is to start its motion from rest. So we have to apply more force to make it move than to continue its motion. Okay, now another example. Find the acceleration of the block, where the same inclined plane is given. Here it is theta, and it is rough, and it is given mu. Now this is mu k. I will consider that this is mu k, because I am giving you that it is slipping. This is not in this theta. This theta is greater than theta r, or angle of repose, or theta is greater than tan inverse of mu. Theta is greater than tan inverse of, or arc tan of mu. Okay. Now we have to find out the acceleration of the block. It is moving in which direction? This direction, with an acceleration of a. Now if you don't understand why it is moving along the plane, then you can watch our constraint series. Although this is very simple, but there I have done with many other cases also. This wedge block constraint, etc. So it is moving down with a acceleration a along the plane, along the inclined plane. Now we have to draw the free body diagram. How to draw the free body diagram? Let's keep this mass, let's separate this mass m. Say mg is acting downwards. I am separating the components of mg. This is mg cos theta, we have done it many times, and this is mg sin theta. And the friction force is acting in the opposite direction. Since it is going down this side, friction force will oppose the relative motion, then it will be acting upwards. So, and normal reaction will be acting perpendicular to the surface. Exactly the same thing I have drawn here. This is normal reaction, this is mg cos theta, this is mg sin theta, and this is f. Now this object is not at equilibrium. It is moving along the plane downwards with an acceleration a. So net force along the plane downwards will be mg minus f, mg sin theta minus f. This mg sin theta minus f will be equal to m into a. But along the, see, perpendicular to the plane, the object is in equilibrium due to the constraint. So due to the constraint of the wedge, or the surface of the wedge, so n is equal to mg cos theta. Simple. This is n, this is mg cos theta, both are equal, because net force on the object is 0. Mg cos theta, that is equal to n. So F is equal to mu n, mu k into n. So in case of static friction, we have to check that it is a maximum or not. Then only we can apply the limiting cases asked or not. Then only we can apply F is equal to mu s into n. But in kinetic friction, it doesn't matter, because the value is constant. It depends only on n and mu k. It is not a self-adjusting force as such. So F is equal to mu k into n, that is mu mg cos theta. See, n is mg cos theta, so mu mg cos theta, mu is mu k. So I am just substituting this value, mg sin theta, mg sin theta. This f I am putting mu mg cos theta, that is m into a. Now we are cancelling out m and taking common g. A is equal to g sin theta minus mu cos theta. I hope so this is clear. So this was an illustration to find out the friction, the acceleration of an object which is encountering friction down the inclined plane. Okay, now the next problem. Calculate the minimum value of f. Calculate the minimum value of f so that the block starts to slip. Okay, this is a block which is kept on a surface that is rough, and the coefficient of static friction mu s is given as mu s. So we are applying a force that is acting with an angle theta with respect to the horizontal. Now we are asked to find the minimum value of f so that the block starts to slip. First, let's understand what this problem is all about. I mean, why the minimum value of f or something like that? Why? What will this angle play? What role will the angle play? See, I am resolving this into two components. This is f cos theta. This is f sin theta. This is mg. This is n. This is the free body diagram I am drawing. And this side, since this f cos theta is trying to pull this side, so friction will act this side, f. Now see, due to this component f sin theta, this normal reaction will decrease. How? Let's write the equation. N is equal to mg minus f sin theta. See, what I can do is that if I increase this f, this normal reaction goes down. If I increase this f, this normal reaction goes down, and we know f max, that is the limiting friction, mu s into n. If I increase the f, then n goes down, then maximum friction holding capacity of the surface also goes down, because this surface will offer less friction to the object. So when I am applying this force with an upward angle, say with angle theta with the horizontal in an upward direction, inclined in an upward direction, then we are making it easier. Suppose we are applying this force like this in a downward direction. So there will be two components. This is the vertical component of the force and this is the horizontal component of the force. Due to this vertical component of the force, the normal reaction will increase. And in fact, our friction offered will also increase from the surface. So there is one thing in the textbooks it is written, it is easier to pull. See, this is pulling and this is pushing. It is easier to pull than to push. It is easier to pull an object than to push an object, because while pulling we will have a component of our force that is definitely not pulling exactly horizontal. We will be pulling something at an angle that is higher than the horizontal. So at a higher level we'll be pulling it from a higher level and we'll pushing it down to from a higher level. So pulling will have a component that will reduce the normal reaction, and pushing will have a component, vertical component, that will increase the normal reaction. So therefore we can say it is easier to pull than to push. Okay, now let's analyze this problem, this particular problem. What is the minimum value of f? See, I have drawn the free body diagram as I have drawn there. This free body diagram I have drawn. Now see, this n is upward and this mg is downward and f sin theta is upward. So n is equal to mg minus f sin theta. As I have already said, this f, if this f increases, then n will increase. If this theta increases, suppose the angle is more upward. Suppose this angle is more upward. So if this theta increases, then also I can say this n decreases. Now what is the friction force offered by the surface. The friction force offered by the surface will be F cos theta. See, F is acting this direction and F cos theta in this direction. So F will be F cos theta. If the question was not given that find the limiting force or limiting angle or anything like that, if the limiting word is not there, then you cannot write F is equal to mu n. Then the friction force will be simply F cos theta. But here it is given limiting, that is why I am writing F is equal to mu n. So mu into mg minus F sin theta. See, n is equal to mg minus F sin theta. So mu into n. So mu into mg minus F sin theta. So again here F cos theta, see F I am replacing by F cos theta, is equal to mu into mg minus F sin theta. So F cos theta plus mu sin theta, I am taking F common. I am taking here mu into F sin theta, I am taking this side. So F cos theta plus mu F sin theta, so I am taking F common. F into cos theta plus mu sin theta, that is mu mg. So lastly we have F is equal to mu mg by cos theta plus mu sin theta. This is the limiting value. This is the minimum value of F we have to provide, and if you can provide greater than this, then the object will start slipping. So this was another application of friction force. Okay, now let's solve a little bit challenging question. A parabolic bowl has the shape corresponding to x square is equal to 3y. We have a parabolic bowl and the shape is x square is equal to 3y. An insect is climbing up the bowl from the bottommost point. Coefficient of static friction is 0.4. Determine how high it can climb. X and y are in meter. So what is exactly asked here? That is, we have a parabolic bowl and it is x square is equal to 3y, and the curve will be like this. X square is equal to 3y. Y is having the power 1, so the symmetry will be around y. Now an insect is climbing up the bowl from the bottommost point. So I have an insect here, and this insect is climbing up like this. How high it can climb? I mean, while climbing, you can see the angle is this angle. It is encountering the angle of the tangent. You can say that the angle is constantly increasing. Here it is something, then it will become like this, then it will become like this. Up to what height can the friction support the insect? See, insect is climbing and the only supporting force it is getting, that is friction. I am assuming that it is getting friction. So how high it can climb, and also I have given the coefficient of static friction. Now we have to calculate. Let's do it. See, this is x square is equal to 3y. It will look like this. Now I am assuming that the insect has climbed up to a height h, and after that it cannot climb any further. See, here what I will do is that I will draw the tangent. If I draw the tangent, I will get an equivalently, I will get an inclined plane, and let this angle be theta. Now what is our strategy to solve this problem? At first we have to formulate a strategy. See, it is going upward, so there is a force mg, that is the weight that will always act. This mg has a component that is mg sin theta, and this component will be mg cos theta. Now what we can say here, that is, since the insect is being pulled by this component mg sin theta, there will be friction that will be opposing this F, and there will be a normal reaction from the surface as well. This normal reaction will be perpendicular to the tangent, because the tangent is giving the approximate the equivalent inclined plane that is climbing up. Only the thing is theta is changing. So this is exactly what we want to find. This is a free body diagram. Now we will find the limiting condition, that is f is equal to mg sin theta, n is equal to mg cos theta. That is the same thing. Okay, see. Before that, can we find this theta with respect to x and y? Because we are not asked to find theta. That is very simple. Theta will be tan inverse of mu. That you can also do. But we are asked to find x and y. So how to make use of the equation of parabola, that is x square is equal to 3y, where y is equal to x square by 3. See, dy dx is equal to tan theta. That is the derivative at a point that will give the tan theta. If you do not understand this part properly, if you have some confusion, then you can see our basic calculus for physics in differentiation and integration, that lecture. In that lecture I have given complete explanation. Now y is equal to x square by 3. So dy dx is 2x by 3. Simple. So now dy dx is tan theta. So tan theta will be equal to 2x by 3. Now let's find theta. See, I have done it here. F is equal to mg sin theta, n is equal to mg cos theta. That is from the free body diagram. F is equal to mu n, mg sin theta is equal to mu n cos theta. See here, mg sin theta is equal to f, n is equal to mg cos theta. So coming here, mg sin theta is equal to mu n cos theta. Definitely this f and this f will be equal in case of limiting case. This is a limiting case, so mu n, so mu is equal to tan theta. This we have already done in case of inclined plane. So here a repetition. Now mu is equal to how much? 0.4. We know mu as 0.4 and tan theta is 2x by 3. So 0.4 is equal to 2x by 3 and x is equal to 0.6 meter. So what is x? So what is x? X is, suppose the insect has climbed up to this height. X is this part. This is x. That is 0.6 meter. But we are asked to find out y. That is the height. So how to find the height? Just put x, the value of x here. I have done it here. So x square by 3, that is 0.6 square by 3, that is 0.12 meter. So the insect can climb up to a height of 0.12 meter. That is the answer. So this required little bit of your analytical skills, but you can easily solve this kind of these questions. Just you have to find the tangent of you have to find the surface, the angle that a surface is making. Exactly, that is the key in this case of this type of questions. Okay, our next question is that find the maximum value of f so that the blocks do not slip. See, this is another question which will test your skills. That is, this is the block M, small m, and this is the capital M block. The small m is 10 kg and the capital M is 40 kg. There is friction between the blocks. The coefficient of static friction is mu s, and it is 0.3. And I am applying a force of F on the upper block. What is the maximum value of this F so that these two blocks will move together? There will be no slipping between M and small m and capital M. Okay, let's start. First, draw the free body diagram. What is the free body diagram here? Let's draw. Draw as many free body diagrams as you can. This will help you master this little skill. This is F, and this is mg. Normal reaction will come from the lower block, that is mass m, and friction will be on this side because it is opposing relative motion. And in case of the larger block, there will be some ground Ng, that is the normal reaction from ground. There is normal reaction from this block, upper block, and there is friction from this friction force, friction from the upper block. There is a horizontal reaction from the upper block, that is friction. So free body diagram we have drawn for both the objects. See, this is the free body diagram. Both are moving with an acceleration a. Just see, both are moving with the acceleration a. For the first object, I can say, see, this mg is equal to n, so n is equal to mg. net acceleration is on the right hand side. So F minus small f, that will be capital F minus small f, will be net force on the right hand side, that is m into a. Now F max, that is mu s into n, because we are asked to find the limiting friction. So let me calculate mu s into m into g. Mu s is 0.3, mass is 10 kg, and g is, let's say, 10 meter per second square. It is given. It is 9.8 or 10, whatever it will be given in the question. I forgot to write, so I am assuming it 10. So it's 30 Newton. Now for the next one, see the next one, this n dash, this mg, these are redundant. We don't need to write this equation because there is no friction down here. So we don't need this n dash. What we need is only the horizontal component, it is small f and a. The only force acting in the horizontal direction, that is small f, that is the friction. This friction is responsible for the movement of this larger block, and if this friction is increasing beyond the limiting friction, that's the maximum friction that these two surfaces can afford as a pair, support as a pair, then there will be relative slipping. Otherwise, this F will move this mass of this block of mass capital M with an acceleration of a. So small f is equal to capital M into a. See, the first equation was capital F minus small f is equal to small m into a, and small f is equal to capital M into a. We add both of them, we will get this f and this f will cancel. F is equal to m plus m into a. So a will be f by m plus m, and this small f is equal to capital F into a, capital M into a. This a I have put here, this a I have put here, f by m plus m, and this small m is capital M, and this value of f, that is a limiting value, mu s into mg. This value we had calculated to be 30 earlier. See here, 30 we had calculated, and now this m into f by m plus m, I am putting the values 40 into f by 40 plus 10. So f is equal to 37.5 Newton I am getting. So this problem could have been given in another way. Let me show you. Suppose they are giving this as 10 kg, they are giving this as 40 kg. The same thing I will be looking at a different angle. Here I will be giving mu is equal to 3, that is mu s. Now they will tell you we are applying a force of say 36 Newton. Find the value of friction acting between the two blocks. Now see, this 36 Newton is less than 37.5 Newton, so definitely these two blocks will not slip. But you don't know actually. Actually, you don't know the value of this friction, this limiting friction, because this is the question that is given to you. So what you have to do in these cases is that you have to take two cases. One is it is slipping or not. So first of all, we are assuming, or we can rather find the maximum value of F so that these two doesn't slip. See, if I ask you to find the friction force F that is acting in between, so what will we do? F minus F is equal to 10A and F is equal to 40A. So I can add them. F is equal to 50A, or A is equal to F by 50. A is equal to F by 50. So small f will be 40A, that is 40 into 40A, that is 40 into F by 50, that is 4F by 5. And what is F? F is here 36 Newtons. So 36 into 4 by 5, it will be 36 into 4 by 5, 144 by 5, that is 28.8 Newtons. Now, if you do like this, you are seeing you have been given mu1, this is 10 kg, so this normal reaction will be 10 g. So F is equal to mu into mg, So 0.3 into say 10 into 10, that is 100, that is 30 Newton. Then this is absolutely wrong. Only in case of limiting friction you can apply this formula, mu is F is equal to mu mg. In case of every other cases of static friction that is lower than the limiting friction, you have to find out the limiting friction and the friction that is acting. Suppose this 36 Newton, that is say 50 Newton. This 36 Newton is now 50 Newton. I am changing it to 50 Newton. Now what will be 4F by 5? 4F by 5 would have been 4 into 40 Newton. This 40 Newton is definitely greater than 30 Newton, that is the limiting. So in that case there will be slipping. Your assumption was wrong. So you will be calculating again. So I think I had made it clear when to apply this formula F is equal to mu n and when not to. And we have to take different cases and calculate. So that's all for today. And stay tuned for problems of higher difficulty level in our problem series for mechanics, which is coming soon. We will be conducting problem series of different difficulty level like level 1, level 2 and level 3. And those problems will be having concepts from multiple chapters or topics, and that will be given along with video solution. So that will be a very interesting series, and whatever concepts we are learning like free body diagram, constraint motion, projectile, then friction and the later topics to come, we will be combine all the concepts and we will be solving some good quality problems that will help you enhance your application skills. So thank you for your patient hearing, and please subscribe our channel and share this video with your friends who are preparing for JEE, NEET or any other exam, or even those who wish to revisit their free body diagram concepts or friction concepts or basic physics. Okay, thank you.